So welcome back to the next video on our series on asymptote. In this video we are going to look at some control flow structures such as if, the for loop and things like that, and functions which allow you to collate repetitive tasks into groups of code where it can be run again and again. And I will highlight some peculiarities that asymptote has with regard to functions, which will come in handy when you want to make more advanced and complicated figures. So let's do some concrete example today. Let's actually draw some polygons and see how we can somewhat automate the process of drawing polygons in asymptote. So as always, I want to just output format PDF. Okay, so this, and then I'm going to make it 5 cm. We can always change the figure size a bit later. So now to draw a polygon, you may recall the from your school that one way to draw a regular polygon, that is a polygon that has equal sides, is to basically just choose the points on a circle, and and the angle between those 2 points is subtended at the center is equal. So one way to do that is to just choose the points as cos 2 pi by n into k and sine 2 pi by n into k. So this is one way to draw the polygons, and that's the way I'm going to do it. So I'm going to define the polygon as a path and then just draw the path. So let's do that. So I'm just going to create a path. So I'm going to path P, and I'm going to define the first point of the polygon. Let's say that corresponds to the point 1 where k is 0. Remember, k goes from 0, 1 up to n. The reason it goes up to n is because it has, you have to want to complete the nth side. So let's actually define our n to be something like, let's say 4 or let's say 5 to make it interesting. And I'm going to define the first point as cos 2 pi into we won't do all this. We're just going to define it as 0, 1 0, because actually if you want me to, let me actually go ahead and say cos 2 pi into k, which is 0, divided by n, and sine of the same thing. Okay, I'm just going to copy paste this. Okay, this is our initial point. Now we want to grow this path to accommodate the other points as well. How do we do that? We can say I is 0, I is less than, let's say, n, and I is equal to I plus 1. So this is a little interesting. This for loop is very similar to the for loop that you find in traditional programming languages like C, C++, and Java. There are some subtle differences which are not going to affect us. So let's go ahead. What I'm going to do is I'm going to grow this path. I can grow it by just using the dash dash operator. Remember, to connect dots, you connect pairs, you need the dash dash operator. I'm going to say P is P hyphen hyphen, and then I'm going to say I'm going to start the I with 1 because I've already have the first point, and I'm just going to copy this. Okay, and then instead of 0 we need to put k. We need to put I over here. So this is going to give me the this is going to give me the path. Okay, I missed this. So what I'm doing is at every point of the loop, when I is 1, you get cos 2 pi by n, sin 2 pi by n. When I is 2, you get cos 2 pi to 2 upon n, sin 2 pi to 2 upon n, and so on. Now all we need to do is to draw P, and that's it. So let's say we say ASY polygon. There is an error. Oh, sorry, I should have said int. Okay, so now, yep, that's built. And now let's open this file open, and I'm going to say polygon.pdf, and let me just zoom out a bit. Yes, we are not yet complete because we have we have to complete the last one because it goes only up to the 5th point. So first, second, third, fourth, and fifth. For the 5th you have to come back. Now there are two approaches. One is you can always you can always just come back and make this less than or equal to, that will complete it. The alternate is you can always just do, I'll show you both. This completes the path, but I also, an equivalent way would be to draw it manually just by putting this as equal to. This will also give you the same result. Okay. So this is a good approach, but the problem is that you can only draw a 5-point polygon with this. If I set this to 6 and rerun it, you get a hexagon, regular hexagon, which is very nice. but we don't want to have to do this repeatedly, by manual change. Let's actually make a function. So let's actually make a function that returns a path. Like I told you, if you know how functions work in C, C++, Java and things like that, it's very easy. All you say is path, let's say gen polygon, and then let's say int n is an argument, and let's then remove this, and then let's put this in the function, and then we'll say return p. And you've created a function. This function returns an object of type path, takes a single integer argument and return, and you can just do this. So for example, let's say draw gen polygon, and we'll say something like 4 just to make some difference. Okay, so you got this diamond, which is actually a square. Okay, if I say 8, you get a nice octagon, a regular octagon. Okay, this is fine, but we want to add some more flavor to our function. Let's actually do a couple of things. If I look at the polygon, right? If I look at this polygon is a regular polygon which has 5 sides. It's a pentagon, but we want to be able to get the pentagon's tip over here, right at the top. For that, you need to rotate this by an appropriate angle. Okay, so you can actually just do something like this. You can do rotate, and remember, rotate is in degrees. So I'm going to do something like 90 upon 5. If you do 90 upon 5 rotation, you basically get the regular polygon. But then this is and for example, if you look at a 4 polygon, right, then you need to do you need to actually rotate it by, let's see, if it's a square, you need to rotate it by 45 degrees. Yeah, it's a square. Okay, because if you don't rotate it by 45 degrees, let's say 0, you get this 45 degree rotated polygon. So for different polygons, you may want to rotate it by different amounts, but that also is not very convenient to do manually. So why not just add it as an argument over here? We'll call it real rot angle. Okay, so this is the second argument. Okay, so the second argument has to be provided now. So for me, for example, if I say something like 45 degrees, okay, oh, I have not used it. So before returning, I just say rotate rot angle. Okay. Now let's just repeat it for the pentagon. For the pentagon, I'm going to require, I think, 90 upon 5 as my rotation. Yep, I get a regular pentagon. If I say 0, I get the old one back. But now, sometimes I may want to rotate it, sometimes I may not want to rotate it, but I don't want to specify it. So one way is to provide a default argument. So I'm going to say a rotation angle is 0, in which case, if I remove this, rotation angle becomes an optional argument because a default value is specified for it. If you do not specify a rotation angle, it is taken 0 as default. However, if you provide the second argument, then that is honored and your polygon essentially rotates. So this makes it very convenient. But now I want to draw a lot of polygons in order, and I want to basically show you how it is. But then if I do something like this, for example, if I draw a polygon like this, and if I draw a 4 quadrilateral and then just do this, right? The problem is that it draws on top of the same, okay, because it's actually just going to draw on top of the same. Instead, it would be much better for me to provide the shift as an argument. For example, I can actually just shift this. Let me shift it by 2.5 units along the x-axis. Sorry about this. Okay, so if I say shift and 2.5, 0, and this should be a pair as an argument to the shift. That's why I had a problem earlier. Now you can see that it shifts nicely. But again, I have to specify it manually for each. Let me just make it an argument to our function. So if I make it an argument for our function, you can say pair shift. You can say shift p. Okay, let's call it shift pair. And after rotation, we just shift it by shift pair star. Now, and we also want to provide the default argument. And default argument is I'll just make this a little smaller, 0 0, so that it is optional. So the existing code is still going to work, but if I now want to shift this, then I can say 0 for rotation, and I can say something at 2.5 comma 0. This is going to shift my quadrilateral 2.5 units to the right. Now you notice that I have set 0 over here. Here is a peculiarity in Asymptote. If you ignore some arguments, Asymptote infers the arguments from the type. So over here I have ignored the second argument, which is rotation angle, which is of type real, and instead I have provided the second argument as a pair. Asymptote then looks through the function declaration and says, okay, the second argument should be a rotation angle. This is not a rotation angle. It's not a real number. It's a pair. Let me go further. The next guy is a pair. So it actually assumes the default argument for this and takes this particular shift P as 2.5 comma 0. So it infers the arguments from the type even if you provide it out of order. If you really want to be explicit, you can also say something like this. This also works. Okay, let me say 3.5 just to prove it to you that this is happening. Even if you ignore the shift P, it will still work. And if you provide an angle, it then takes it. Okay, of course, 45.0 will ensure that it is being treated as a real. So you can actually just make these changes and observe it. So let's actually draw a family of polygons using this approach that we have. Let's say I go from triangle onwards and I stop at, let's say, decagon, a regular decagon. Okay, so for int I is equal to 0, I is less than or equal to 10, I is equal to I plus 1. Okay, let me close this brace, and now I'm going to say let me not start at this. I'm going to start at a triangle. So now if I want to draw a triangle, I'm going to just say draw gen polygon. Okay, and I need 3 sides. Okay, I don't want rotation angle. I'm just going to shift it. I'm going to shift it by 2.5 times I minus 3 comma 0. I'm going to shift it by 2.5 units. Okay, and let me then also draw provide a label which indicates n. So how do I do that? I'll say $n is equal to, and then I'll just add a plus. Remember, I can add strings, I can concatenate strings, and I'm going to cast this I, and where does this go? This is going at the same location. Maybe I'll just say the x coordinate will be the same. I'll go -1 unit so that it's below this can be, and this is it. So now let's have a look at how this works. Oops, yes, I should have added a plus over here, of course, to concatenate, and shift P should not be like this. It's automatically taken. So now, okay, so the problem is that the size is too small. Let's actually make the size a little bigger. Let's make it 15 centimeters. Okay, and let's bring this, let's bring the label little further below. Let's make it minus something like 1.5, and you can see that we have a nice family of polygons. Let me make this bigger for you. So you can see that we have a nice family of polygons, and it's equal to 3, 4, 5, 6, 7, 8, 9, and 10. And this for loop essentially takes care of all the hard work for us. If you want to rotate everything by the same amount, it's very easy. You can just say something like 90. It's going to rotate things by 90 degrees. Okay, it looks good for many of them. Okay, you can find out why 90 is a good rotation. It's very clear. Or if you want to rotate it by some other angle also, 45. Okay, you can get some other looks as well. So in this manner, you can write functions. Functions have some peculiarities which you can check out in the documentation, but Asymptote is very powerful in allowing you to automate these functions. And in future videos, we are going to look at how you can use these advanced features to make some more interesting shapes as well as reduce your efforts. So let me just make this 90, and then we're back at where we were, and let me stop it here. So please give your comments if you have any questions, and thank you so much.